We now turn our attention to the concept of limit. What does it mean for a function to have a limit? Consider the following function, x squared minus x plus 2. It is a quadratic function, and here is the graphical representation of this function. What happens to the values of f of x as x gets closer to 2? How does this function behave when x is approaching the number 2? Let's start at 1 and walk toward 2 on the x-axis.
F of 1 is 1 squared minus 1 plus 2, which is 1 minus 1 plus 2, which equals 2. If x is 1.5, so we substitute the value 1.5 for x in the expression of f of x, which is 1.5 squared minus 1.5 plus 2. And this equals 2.75. We started at x equal 1, and then 1.5, 1.8, 1.9, 1.95, 1.99, and so x is getting closer and closer to 2. And if you look at the second column, the values of the function are getting closer to a specific number, which appears to be 4, right? We go from 2 to 2.75 to 3.44, 3.71, 3.85, 3.97, 3.98, 3.99, and if we keep doing this, we'll probably reach the value 4.
As x gets closer to 2 from the left, it appears that the function values are getting closer to 4. But what happens if we approach 2 on the x-axis from the right? Using a calculator, Oliver computed the values of f of x for 3, 2.5, 2.2 till 2.001.
When x is 3, f of x, which equals 3 squared minus 3 plus 2, 9 minus 3 is 6 plus 2, equal 8. Right? For 2.5, f of x is 5.75, 2.2, 4.64, and it's very clear from the table, on either side, from the left or from the right, the function is getting closer to 4. We have 3.99 from the left and 4.003 from the right. If this graph represents a function f of x, the limit as x approaches a of f of x equal the value L. And some people might also write it as f of x arrow L as x arrow a. So roughly speaking, this is saying that the values of f of x tend to get closer and closer to a specific number L as x itself gets closer and closer to the number a, from either side of a, from the left or from the right.
Guess the limit of x minus 1 divided by x squared minus 1 as x approaches 1. With your calculator, compute the values of f of x for values of x close to 1.
F of x is x minus 1 over x squared minus 1. If we start with 0.5, we have 0.5 minus 1 divided by 0.5 squared minus 1, which is 0.66667.
On the basis of the table values, we make the guess that the limit is 0.5. Let us now look at the limit from the right-hand side.
Starting at 1.5, right, and 1.1, 1.01, 1.001, 1.0001. F of 1.5 is 1.5 minus 1 divided by 1.5 squared minus 1, which is 0.4. f of 1.1, which is 1.1 minus 1 divided by 1.1 squared minus 1, is 0.47619. f of 1.01 is 0.497512.
Using a calculator, Oliver computed a few values of f of x with 6 decimal places as x approaches 1 from the right. On the basis of these values, we can also guess that the limit is 0.5.
And so it may seem that this function has a limit and that the limit is 0.5. And in fact, if you look at the graph of f of x, it is very clear that when x gets near 1, from either side of 1, without actually being equal 1, f of x gets closer and closer and closer to 0.5.
Let's do some practice. Estimate the value of the limit of the function square root of t squared plus 9 minus 3 divided by t square as t approaches 0. Using your calculator, compute the values of f of t for 1, 0.5, 0.05, 0.01, etc.
f of 1 is root of 1 squared plus 9 minus 3 over 1 squared, which is root of 10 minus 3 divided by 1, and this is approximately 0.16228. Alright, that's f of 1. f of negative 1 is square root of negative 1 squared plus 9 minus 3 divided by negative 1 squared, which is root of 10 minus 3 divided by 1, or 0.16228. When t is plus minus 0.5, f of t is 0.16553.
It would seem from the table that the function values are approaching 0.1666 as t gets closer and closer to 0.
And this value is an approximation of the fraction 1 over 6. And so we guess that the limit when t approaches 0 of f of t equal root of t squared plus 9 minus 3 over t squared is 1 over 6.
Can you guess the limit of sine x divided by x as x approaches 0?
Now for f of x equals sine x divided by x, make sure your calculator is operating in mode radian. F of 1 will then be sine 1 divided by 1, which is close to 0.84. F of 0.5 sine 0.5 radian divided by 0.5, which is 0.958.
The values of sine x over x are getting closer and closer to 1 as x gets closer to 0. So we can guess that the limit is 1.
F of x equals sine x over x is approaching 1 as x is approaching 0.
This is very obvious from the graphical representation. Indeed, whether we approach x from the right or from the left, sine x over x is approaching 1. It would seem that computing a few numerical values of a function is enough to get the limit of that function. But this is not true.
In order to show that this is not always the case, consider the following function. F of x equal to sine pi divided by x. Okay, so let's try f of 1 over 2, f of 1/3. Okay, f of 1 is sine pi divided by 1, which is 0. F of half is sine pi divided by half, which is actually sine 2 pi, which is 0. F of 1/3 is sine pi divided by 1/3, which is sine 3 pi, which is also 0. All these values are equal 0. So on the basis of this information, we might be tempted to guess that the limit as x approaches 0 of sine pi divided by x equal to 0. This is our best guess based on these values. But this time the guess is wrong.
To see why this guess is wrong, consider the graphical representation of this function. Look at the behavior of f of x as x is near 0. The function is behaving very strangely. It is oscillating from the left or from the right.
So there's no fixed value of f of x, right, as x gets closer and closer to 0, which also means there's no limit.
The lesson to take from this example is that there are always pitfalls when you try to get the limit of a function from a few numerical values.
So this limit is dne.
It is very easy to guess the wrong value if you use inappropriate values of x. Sometimes calculators and computers give the wrong value.